Hello, everyone. My name is Juan Pablo González Zazueta from the University of Sonora, Mexico. And today I'm going to present this work that I made with my professor, Julio César Saucedo Morales, which is comparison of eclipse predictions with the Antikythera mechanism and the Maya methods. This, by using Python and NASA's 5 Millennium Catalog of Solar Eclipses, we identified and compared Osiris series with SPANX data, extending the analysis to Maya, Inex, and Tritos cycles. We evaluated the accuracy of the Maya 11,960-day cycle and analyzed statistical patterns in eclipse intervals. Moreover, we adapted the Archimedean spiral in the Antikythera mechanism to this cycle that enabled the visualization of distinct eclipse patterns. So just to put in context with this civilization, with this ancient, well, the Mayas stand out as one of the most advanced Mesoamerican civilizations because over millennia, they developed independent city-states, commercial networks, and the famous hieroglyphic writing systems, and in particular, calendars and astronomical knowledge of notable accuracy. So this approach also vindicates the diversity of knowledge in human history. In this image, we can see El Caracol, which is the Mayan observatory of Chichen Itza in the southern Mexico. Okay, so where was the Maya zone? Well, they were located in the Yucatan Peninsula in southern Mexico. In this map, we can see the Maya geographic zone. And just a little bit about their history. The apogee of the Maya culture occurred during the Classic period from 2000 to 900 of the Common Era, when it reached its peak of splendor. So the Maya used basically three dating systems, which consisted of three calendars: the sacred or Tolkien calendar, comprising 260 days, the civil or half calendar, comprising 365 days, and the third one is the astronomical calendar or land count, forming a 52-year cycle. So how did the Maya actually count? Well, they used a vigesimal numbering system that consists of bars, dots, and a shell, which are organized into positional levels based on powers of 20 to represent large numbers. So, for example, if we want to count from 0 to 19, we would use from 1 to 4 dots in a row. And if we want to count for if we want to use the 90 number, for example, we would use in a row 4 dots and about 3 bars above one about 4 dots above these 3 bars. But if we want to count larger numbers, we will use the positional level of powers of 20. And for example, for the first level, we would multiply by 1. For the second level, we will multiply by 20. And for the third level, we will multiply by 400 and so on. But there is a specific detail that for chronological counting, the second position is 20, by which we would be 20 by 20, but the Maya used 360 instead of this 400. This was because they wanted to approximate the 360 to the 365 days of their half calendar.
Okay.
When talking about the Maya records, we can say that the most important is the Dresden Codex and the Maya cycle. The Dresden Codex is of great importance for this study to the eclipse table that it contains, because it is a record that talks about their counting in a span of 11,960 days, which is the Maya cycle. So some researchers date this specific codex to between 1,200 and 1,250 of the Common Era. And this table, as I mentioned before, spans a duration of 11,960 days, which is equally which is equivalent to 405 lunations or 69 short eclipse cycles. And this period covers nearly 33 years or 46 Tolkien cycles, which is the second calendar that I mentioned Maya used to count time. And it is also a time frame commonly referred to as the Maya cycle. And it contains cumulative counts of 148, 177, and 178 days. This image is the first page of the Dresden Codex Eclipse Table, but here we have the Dresden Codex Complete Eclipse Table. And the Maya timekeepers adopted the lunar count with alternating 30-day to 90 to 29 days, lunar months. So 6 lunar months always amounted to 177 or 178. And this is because the Maya didn't use real numbers, so they used even numbers. So they would count, they would alternate from 177 to 178 to fix this accumulation of day fractions. And about the Greek methods, well, the Greeks used an Archimedean spiral to calculate eclipses. They employed a 4-turn spiral to represent 223 lunations of the Saros cycle. And this is an image that is on the Antikythera mechanism replica, the MAM, that we saw before. And they have dimensions about 1 meter by 1 meter. About the methodology, we used the NASA database that was the 5 Millennium Catalog of Solar and Lunar Eclipses elaborated by Fred Spenak, and it contains eclipses that occur in 5,000 years, and that comprises from the year minus 1999 to 3000. And this is the main algorithm flowchart, because we designed a special algorithm to calculate an eclipse cycle sequence in order to find eclipse series. This was done by using the previous NASA database. I'm going to explain it to you briefly. So we start, and then we enter a cycle, whatever the cycle we want. For example, the Saros cycle, the Maya cycle, Trato cycle, Inc cycle, to and an initial date. So we add the cycle and obtain a date, a new date. Then we need to verify if that date exists in our database. If yes, we just record. If no, we add an error margin of 2 days to verify the existence of this date. If no, we return to a previous date that was correct just to verify if there was an eclipse duo. But what is an eclipse duo? An eclipse duo is a pair of eclipses that has a difference of 29.53 days, which is the duration of a synodic month, because we found it that at the start of an end of every eclipse series, we have an eclipse duo. So if we found an eclipse duo, we would just continue with the algorithm. If no, then we have to end this algorithm, and we need to verify if it has the minimum number of elements. If no, we discard it. If yes, we just write the data. And results. Well, basically, we got the same Saros series, which demonstrates the correct operation of the code. These series are Saros numbered from 27 to 150, with the exception of series that contains dates which are unavailable in database. This histogram is of Saros period values. Is the distribution of Saros period values we obtained from family 20 to 7, and we can see that the mean value is around 6,585.32 days, which is basically the mean value, the conventional mean value for the Saros period. Here we have the histograms of the short eclipse periods that we calculated. On the left side, we have the calculated values above the Dresden Codex values. And if we compare it, we have the difference between the obtained mean values and the Dresden-Cotes values, and we obtain just small differences that prove the accuracy of results. Here we have the discrepancies of in short period eclipse intervals, SPENAC versus Dresden-Cotes, and we obtain a mean value for the Maya cycle of 11,959.86 days, which is so close to the 11,960 days. And summing it up, the Maya eclipse series that we obtained, we have 174 files with Maya series that were delimited either by pair eclipses or by their start and end points. And this resulted in 477 Maya series. The range for the number of eclipses per series is 16 to 24, with a duration range to 491 to 720 years. And in the left side, we see that the chart of the distribution of number of members by series, it is around 20 eclipses per Maya series. And this kind of chart is really interesting because we can see the maximum eclipse duration as a function of time for a series categorized by eclipse types. Every color represents a different kind of eclipse, which it could be total, partial, annular, hybrid, and so on. This is for the series of solar eclipses. And here is for a Maya series of solar eclipses, which obviously has a less amount of eclipses because of its characteristics. But if we can see that it has a similar form, but with less eclipses compared to the Saros series. And this Archimedean spiral for Saros cycle is the adaptation that we did use, that we were inspired by the Antikythera mechanism, which is on the right side of the Antikythera mechanism replica. So we adapted to any other cycle that you want to represent. For example, on the left side, we have the Saros spiral with the Antikythera mechanism sequence, where the sigma represents lunar eclipses and the letter eta represents solar eclipses. Here is for the Metonic cycle, which forms a different pattern. And this is just an arbitrary sequence of solar eclipses, which they're every kind of eclipse. Just wrote it with a small letter, partial, total, annular, and etc. This is for the solar eclipse of April 8th in 2024. And this is the same, but for the Inex and the Maya cycle. So I have to mention that adapting this spiral to any other eclipse cycle, we had to add an extra synodic month when we need it. For example, the Saros cycle is 223 synodic months, and every single grid cell in this spiral represents a synodic month or a lunation, but we want it to be divisible by an even number. For example, in the Saros spiral, we would add an extra grid cell of one synodic month, so we would have 224 synodic months divisible by 4, because the spiral also is in function of an angle. So we would we would have every single eclipse marked with their specific angle, which is approximated because obviously it's not a circumference, it's a spiral, so it's just an approximation of an angle. So this is a spiral chart for the Maya cycle, and this is a proposal for the Antikythera mechanism sequence that we find in the literature, which is the December 22 in the year of minus 177. And finally, we proposed the start days of the Dresden Codex, which were actually 5. Here I will show you 2 of them. The red color is for the Dresden Codex eclipsable sequence, and the black color is for the sequence that we found it in with the algorithm. So our conclusions are that the algorithm successfully reproduced the established Saros cycle series, which validates the program's computational accuracy, and that the Maya cycle is a good predictor for solar eclipse families, and that by adapting the Saros spirals concept with 5 initial days were proposed for the Dresden Codex table, that the eclipse series starts and then occur in eclipse duos, and that the Maya astronomical knowledge comprises complex systems for eclipse recording and prediction, proving that their mathematical sophistication and accuracy. This is...
Okay. Thank you very much. Ευχαριστούμε πολύ τον Juan Pablo González για αυτήν την ευκαιρία που είχαμε να ακούσουμε για τους Μάγια, για τις εκλήψεις, για τις μεθόδους τους. Thank you very much, Juan Pablo.